Hello and good day. Gentlemen. My name is Shahid Khan and I am a chemical engineer. I have prepared a training course on compressors. This course will refresh your knowledge on compressors. This course is beneficial for all personnel from operators to engineers who are working with compressors. After completing this course, you will be able to explain the principles of compression. Describe how centrifugal compressors operate. Describe how axial flow compressors operate. Identify and describe centrifugal and positive displacement compressors. Identify the basic components of a rotary screw compressor. Describe the operation and basic components of sliding vane compressors. Explain how lobe compressors operate. Describe how liquid ring compressors operate. Explain the scientific principles associated with reciprocating compressors. Identify the basic components of a compressor system. Start up and shut down a positive displacement compressor. Start up and shut down a dynamic compressor. Before starting the course, let's have a look on key terms of compressors. Aftercooler is a heat exchange device designed to remove excess heat from the discharge side of a multistage compressor. Centrifugal compressor uses centrifugal force to accelerate gas and convert energy to pressure. Compression ratio is the ratio of discharge pressure, PSIA, to suction pressure, PSIA. Multistage compressors use a compression ratio in the 3 to 4 range, with the same approximate compression ratio in each stage. For example, if the desired discharge pressure is 1500 psia, a 4-stage compressor with a 3.2 compression in each stage might be used. The pressure at the discharge of each stage would be: first equals 47 psia, second equals 150 psia, third equals 480 psia, fourth equals 1536 psia. Demister is a cyclone-type device used to swirl and remove moisture from a gas. Desiccant dryer is used to remove moisture from compressor gases as they are passed over a chemical desiccant, which absorbs the water. Diaphragm compressor utilizes a hydraulically pulsed diaphragm that moves or flexes to positively displace gases. Double-acting compressor is a reciprocating compressor that compresses gas on both sides of the piston. Dryer removes moisture from gas. Intercooler is a heat exchange device designed to cool compressed gas between the stages of a multistage compressor. Lobe compressor is a rotary compressor that contains kidney bean-shaped impellers. Oil separator removes oil from compressed gases. Receiver is a compressed gas storage tank. Stage is each cylinder in a compressor, specifically, the area where gas is compressed. Thermal shock is a form of stress resulting in metal fatigue when large temperature differences exist between a piece of equipment and the fluid in it. Compressor applications and classification. The compression of gases and vapors in the process industry is very important. Compressors are used in a variety of applications. In a modern plastics facility, compressors are used to transfer granular powders and small plastic pellets from place to place. In natural gas plants, compressors are used to establish feed gas process pressures. Compressors also provide clean, dry air for instruments and control devices. In a refinery or chemical plant, compressors are used to compress gases such as light hydrocarbons, nitrogen, hydrogen, carbon dioxide, and chlorine. These gases are sent to headers, from which they are distributed to a variety of applications. There are 3 basic designs for compressors as shown in picture: dynamic, positive displacement, and thermal. Dynamic compressors include centrifugal or radial flow and axial, straight line, flow compressors. Positive displacement compressors include rotary and reciprocating compressors. Dynamic compressors accelerate airflow by drawing air in axially and spinning it outward, centrifugal compressors, or in a straight line, axial flow compressors. Positive displacement compressors compress gas into a smaller volume and discharge it at higher pressures. Thermal compressors use ejectors to direct high-velocity gas or steam into the process stream, entraining the gas, and then converting the velocity into pressure in a diffuser assembly. This chapter focuses primarily on dynamic and positive displacement compressors. A compressor is part of a much larger system. The system's resistance to flow typically dictates compressor performance. Minor problems are occasionally experienced with compressor systems. These troubles are usually the result of dirt, adjustment problems, liquid in the system, or inexperience in operating the system. Experienced technicians can quickly fix the problem by making the proper adjustment, cleaning the equipment, replacing a minor part, or removing an adverse condition. The principles of compression are: gases and vapors are compressible. Compression decreases volume. Compression moves gas molecules close together. Compressed gases will resume their original shape when released. Compressed gases produce heat because of molecular friction. The smaller the volume, the higher the pressure. Force divided by area equals pressure. Gas volume varies with temperature and pressure. Liquids and solids are not compressible, except under tremendous pressures. Dynamic compressors. Dynamic compressors are classified as either centrifugal or axial flow. Both types operate by changing the velocity of gas and converting energy to pressure. Centrifugal compressors. During operation, gas enters a centrifugal compressor at the suction inlet and is accelerated radially by moving impellers as shown in picture. Centrifugal compressors have one moving element, the driveshaft and impeller. In a centrifugal compressor, the impeller discharges into a circular, narrow chamber called the diffuser. This narrow opening completely surrounds the impellers. As back pressure builds in the impeller, gas velocity is accelerated through the diffuser assembly and into a circular volute. As high-velocity gas moves through the diffuser and into the volute, kinetic energy is converted into pressure as gas speed slows in the ever-widening volute before exiting the discharge port. Because compressor performance is linked to the compressibility of the gas it is moving, centrifugal compressors are more sensitive to density and fluid characteristics than are reciprocating compressors. Most centrifugal compressors are designed to operate at speeds in excess of 3,000 rpm. Recent advances in technology have resulted in the development of a centrifugal compressor that runs at speeds in excess of 40,000 rpm. Centrifugal compressors can be single-stage or multi-stage. Single-stage compressors as shown in picture compress the gas once, whereas multi-stage compressors deliver the discharge of one stage to the suction of another stage. Single-stage centrifugal compressors are designed for high gas flow rates and low discharge pressures. Multi-stage compressors are designed for high gas flow rates and high discharge pressures. Centrifugal compressors are also used for transferring wet product gases that typically damage positive displacement compressors. Compression ratio. Compression ratio is defined as the ratio of discharge pressure, PSIA, to suction pressure, PSIA. Frequently, the desired discharge pressure is very high, over 100 times that of the inlet pressure. When a gas is compressed, the temperature of the gas increases. If a gas was compressed in one stage to a pressure 100 times that of the inlet pressure, the gas temperature would be extremely high. Multi-stage compressors, with cooling between stages, are used to develop high pressures to allow for the heat of compression. The compression ratio normally runs in the 3 to 4 range, with the same approximate compression ratio in each stage. For example, if the desired discharge pressure is 1,500 psia, a 4-stage compressor with a 3.2 compression in each stage might be used. The pressure at the discharge of each stage would be: first equals 47 psa, second equals 150.5 psa, third equals 481.7, fourth equals 1541.4 psa. The simple calculation used to calculate the pressure increase on each stage is Stage 1 14.7 psax 3.2 is equal to 47.04 psia. Stage 2 47.04 psax 3.2 is equal to 150.528 psia. Stage 3 150.528 psax 3.2 is equal to 481.689 psia. Stage 4 481.689 psax 3.2 is equal to 1541.407 psia. The basic components of a centrifugal compressor are shown in picture. The part of the impeller vane that comes into contact with gas first is called the suction vane tip. The part of the impeller vane that comes into contact with the gas last is called the discharge vane. The driver is an electric motor or turbine. The basic types of impellers used on centrifugal compressors are the open backward-bladed impeller, open radial-bladed impeller, and closed backward-bladed impeller. This picture illustrates various impeller designs. Centrifugal compressors are considered to be the workhorses of the chemical processing industry. They are chosen more often than other types for new installations because they have a very low initial installation cost, low operation and maintenance cost, simple new piping installations, interchangeable drivers, large volume capacity per unit of plot area, and long service life. In addition, they can deliver much higher flow rates than positive displacement compressors. Axial flow compressors. In the industrial environment, axial compressors are the compressor of choice for jobs where the highest flows and pressures are required. Unlike centrifugal compressors, axial compressors do not use centrifugal force to increase gas velocity. An axial flow compressor is composed of a rotor that has rows of fan-like blades as shown in picture. Airflow is moved axially along the shaft. Rotating blades attached to a shaft push gases over stationary blades called stators. The stators are mounted on or attached to the casing. As the rotating blades increase the gas velocity, the stator blades slow it down. As the gas slows, kinetic energy is released in the form of pressure. Gas velocity increases as it moves from stage to stage until it reaches the discharge scroll. Multistage axial compressors can generate very high flow rates and discharge pressures. As a general rule, an axial compressor requires twice as many stages as a centrifugal compressor to perform the same operation. However, axials are 8% to 10% more efficient. Axial compressors are limited to approximately 16 stages because of temperature and equipment stress. Axial flow compressors are often used in series flow with centrifugal compressors because they are capable of operating at greater capacities. The primary application of axial compressors involves the transfer of clean gases such as air. The internal components of an axial flow compressor are extremely sensitive to corrosion, pitting, and deposits. The stator blades in an axial compressor can be fixed, individually adjustable, or continually variable. Individually adjustable stator blades can be adjusted from outside the casing. Continually variable blades are adjusted by a drive ring linked to a driveshaft that is automatically actuated by a power cylinder. In contrast to a centrifugal compressor, axial compressors accelerate and compress gas in a horizontal, straight-through motion, without the turbulent changes in direction characterized by centrifugal compressors. Pound for pound, axial compressors are lighter, more efficient, and smaller than centrifugal. A 23,000 horsepower axial produces as efficiently as a 25,500 horsepower centrifugal. Even so, axial flow compressors are not as common as reciprocating and centrifugal compressors. One main use of axial compressors is in gas turbine applications. Blowers and fans. Blowers and fans are simple devices typically classified as compressors. The two basic designs are axial flow and centrifugal flow. Most blowers and fans are single-stage devices designed to perform a specific function. Single-stage, centrifugal blowers are used for low-pressure air systems, refrigeration units, leaf blowing, ventilation systems, or laboratory hoods. Fans can be used to direct airflow into or out of industrial equipment such as cooling towers, flares, boilers, furnaces, HVAC, heating, ventilating, and air conditioning systems, or air-cooled heat exchangers, or they can be used for ventilation of confined spaces. Fans can be classified as centrifugal, propeller, tube axial, or vane axial. Centrifugal fans are designed to move gases over a wide range of conditions. Propeller fans consist of a propeller and a motor mounted on a ring. This fan is primarily designed to operate over a wide range of volumes at low pressures and to move air from one enclosed area into another. Tube axial fans are mounted directly in the piped cylinder and are designed to move air or gas at medium pressures. The vane axial fan resembles the tube axial fan. The motor and fan are mounted directly in the tube. A series of vanes help direct flow over a wide range of volumes and pressures. Each of these 4 fans can be direct drive or belt driven. Positive displacement compressors. Positive displacement compressors operate by trapping a specific amount of gas and forcing it into a smaller volume. They are classified as either rotary or reciprocating. Rotary compressors are further classified as rotary screw, sliding vane, lobe, or liquid ring. Reciprocating compressors are classified as piston or diaphragm. Positive displacement compressors remove a set volume of gas for every rotation or stroke of the primary transfer elements. In process systems where fluid density and suction pressures vary, positive displacement devices provide steady service. Rotary compressors can deliver pressures between 100 and 130 psia. Reciprocating compressors discharge pressures that range from 0 to 30,000 psig. Rotary compressors. Rotary compressors take their name from the rotating motion of the transfer element. A good case could be made that centrifugal compressors are rotary. Centrifugal compressors do rotate, but they do not positively displace or compress the gas. In contrast, the rotating elements of a rotary compressor displace a fixed volume of fluid inside a durable casing on each rotation. Rotary screw compressors. The rotary screw compressor is commonly used in industry. This device closely resembles the lobe compressor and operates with 2 helical rotors that rotate toward each other, causing the teeth to mesh as shown in picture. As the left rotor turns clockwise, the right rotor rotates counterclockwise, forcing gas to become trapped in the central cavity. Rotary screw compressors are designed with an inlet suction line and an outlet discharge port. The 2 rotors are attached to a drive shaft, timing gears, and a driver that provides the energy to operate. Flow enters the device and is moved axially toward the discharge port. The majority of compression takes place very close to the compressor outlet. The moving elements of the rotary screw compressor do not touch each other or the inner wall. A set of timing gears allows the power rotor to turn the alternate rotor. Because of this design, the rotating elements do not require lubrication, making them a perfect choice for dry gas service. Because of the small tolerances that exist between the moving elements, some internal slip occurs during operation. Rotary screw compressors operate at speeds between 1,750 and 3,600 rpm and have capacity ratings above 12,000 cfm, cubic feet per minute, on the inlet volume and discharge pressures between 3 and 20 psig. Some rotary screw units can operate between 60 and 100 psig. Another feature associated with the rotary screw compressor is its ability to be used as a vacuum device. This system is designed to handle 500 to 10,000 cfm on the suction side and to pull a vacuum between 5 and 25 inches of mercury. Sliding vane compressors. The sliding vane compressor uses a slightly off-center rotor with sliding vanes to compress gases. The major components of a sliding vane compressor are shown in picture. The gas inlet port is positioned so that gas flows into the vanes when they are fully extended and form the largest pocket. As the vanes turn toward the discharge port, the gases are compressed. The body of the compressor is fabricated from cast iron or steel. A set of cooling water jackets is fabricated into the initial design and tested for tightness. The rotor and shaft are made of high-strength alloy steel. The rotor is precision-made with slots around the entire rotor. The sliding vanes are composed of asbestos phenolic resin, metal, or high-temperature, durable metal. Sliding vane compressors require lubrication between the vane and contact surface. Lubricating oil is injected into the suction side of the compressor. This procedure helps prevent internal slip and provides a positive seal. Sliding compressors are typically non-pulsing systems. As gas enters the sliding vane compressor, it is captured in vanes and swept around the casing, filling the chamber. As the vanes rotate toward the discharge, the vane length shortens because of the rotor's eccentric position with the shaft, and volume is decreased. As volume decreases, pressure increases until maximum compression is achieved. At this point, the gas is discharged out of the compressor. This type of compressor does not use suction or discharge valves because it is designed to discharge against system pressure. Lobe compressors. Lobe compressors are characterized by the two kidney bean-shaped impellers used to trap and transfer gases as shown in picture. The close clearances between the casing and impellers are maintained by a set of timing gears. During operation, the two impellers move in opposite directions on parallel-mounted shafts as the lobes sweep across the suction port. The parallel shafts are composed of a drive shaft and an idler shaft. The drive shaft forces the idler shaft to turn through the gears. The gears and bearings are located on the outside of the compressor. Compressed gases are released to the discharge line. The internal lobes on a rotary lobe compressor are designed not to touch. A few thousandths of an inch clearing exists between the casing and lobes. The design clearances on the internal lobes of a lobe compressor allow some slip. The slip is aggravated at high discharge pressure when low-density gases are being pushed. Process slip is constant only when system pressure is constant. Lobe compressors are designed to have constant volume discharge pressures and constant speed drivers. Lobe compressors do not use discharge or suction valves because they are not designed to operate at a specific pressure. Discharge pressures are determined by the system's process pressure. Lobe compressors can be used in wet and dry gas service. The rotation of the lobes may be up or down, that is, the discharge port can be at the top or at the bottom of the unit. In dry service, the upward rotation is preferred. In wet service, the downward rotation is recommended so any condensed liquids can escape. Lobe compressors can be used as compressors or vacuum pumps. Liquid ring compressors. A very unusual compressor design is the liquid ring compressor. It combines the centrifugal action of the liquid with a positive displacement, rotary action. A liquid ring compressor has one moving transfer element and a casing that is filled with makeup water or seal liquid as shown in picture. As the rotor turns, the fluid is centrifugally forced to the outer wall of the elliptical casing. An air pocket is formed in the center of the casing. As the liquid ring compressor rotates, a small percentage of the liquid escapes out the discharge port. Makeup water or seal liquid is admitted into the compressor during operation. The liquid medium helps cool the compressed gases. The off-center position of the rotor creates an offset in the air pocket. Located on the rotor are suction and discharge ports. The inlet ports are much larger than the discharge ports. As the vanes turn, gases are compressed in the volute-shaped air pocket. Liquid ring compressors may be found in the following applications: hazardous gases, toxic gases, hot gases and vapors, vacuum of 27 to 29 inches of mercury, non-pulsing flow, jet and surface condenser, oil-free gases. Scroll compressors. A scroll compressor as shown in picture has two interleaved spiral vanes designed to compress fluids into ever-decreasing volumes. Scroll compressors run quietly and smoothly at lower volumes, trapping fluid between the scrolls. In most cases, one scroll is fixed and one orbits eccentrically without rotating. Reciprocating piston compressors. Their distinctive back-and-forth motion characterizes reciprocating compressors. Reciprocating compressors are classified as either piston or diaphragm. Diaphragm compressors utilize a hydraulically pulsed diaphragm that moves or flexes to positively displace gases. We discuss only the piston type because it is the most popular design. Equipment ratings from fractional horsepower to over 20,000 horsepower are possible on reciprocating compressors. Pressure differences of below atmospheric on the suction side to over 30,000 psia on the discharge side are possible. During operation, reciprocating compressors perform best with clean gases. Entrained water, dirt, and impurities will cause excessive wear on the piston and cylinder. Reciprocating compressors are selected when low flow rates and high discharge pressures are required. There are several advantages of using a reciprocating piston compressor. They have a flexible pressure range and overall capacity, low power cost, and high efficiency rating. They can handle density and gas composition changes and small volumes and can deliver high pressures. Reciprocating piston compressors work by trapping and compressing specific amounts of gas between a piston and the cylinder wall. The back-and-forth motion incorporated by a reciprocating compressor pulls gas in on the suction or intake stroke and discharges it on the other. Spring-loaded suction and discharge valves work automatically as the piston moves up and down in the cylinder chamber. The basic parts of a reciprocating piston compressor are shown in picture. Reciprocating piston compressor design varies from model to model. These variations usually occur in the total number of cylinders and in the arrangement of the suction and discharge lines. Most piston compressors have 1 to 4 cylinders. Each cylinder has its own piston, rings, and automatic valves. Common crankshafts can be shared with multiple connecting rods. The same cylinder can be equipped with multiple suction and discharge valves in double-acting compressors. Cylinder design. A cylinder's material is typically selected on the basis of corrosion resistance, thermal shock resistance, pressure rating, and mechanical shock resistance. Thermal shock is a form of stress resulting in metal fatigue caused by large temperature differences between a piece of equipment and the fluid in it. Common materials used to fabricate cylinders are cast iron, up to 1,200 psig, nodular iron, 1,500 psig, cast steel, 1,200 to 2,500 psig, and forged steel, over 2,500 psig. Single-acting parallel arrangement. In a parallel cylinder arrangement as shown in picture, 2 cylinders are lined up. They have separate intakes and a common discharge line. This type of operation doubles the flow rate while keeping the pressure constant. Single-acting multi-stage compressors. A multi-stage piston compressor has 2 or more cylinders. The first cylinder usually is referred to as the first stage. 2-stage multistage compressors as shown in picture discharge from the first cylinder into the suction line of the smaller second cylinder. In a multistage compressor, flow rates usually are low and overall pressure is high. Double-acting compressors. Double-acting compressors as shown in picture use a common cylinder and piston to discharge and take in gases on each side of the cylinder. Double-acting compressor cylinders are equipped with 2 spring-loaded intake valves and 2 spring-loaded discharge valves. For example, when the piston moves to the right, the chamber to the left of the piston fills with gas, while the chamber to the right of the piston discharges. The exact opposite occurs on the reverse stroke. This technology doubles the efficiency of the compressor. Compressor layout. The layout of a compressor can be determined easily by looking at the position of the cylinders. V and L-shaped layouts are found frequently as shown in picture. Pulsation control. A common problem found with reciprocating compressors is pulsation. This inherent problem occurs because the suction and discharge valves open and close during each cycle. This problem can be controlled by using a surge drum, pulsation dampener as shown in picture, or volume bottle. These devices provide smooth gas flow, reduce vibration, and prevent overloading or underloading the compressor. Diaphragm compressors. Diaphragm compressors utilize a hydraulically pulsed diaphragm that moves or flexes to positively displace gases. This type of compressor is closely related to a reciprocating compressor. This type of compressor is a combination of several systems, a gas compression system and a hydraulic system. Gas compression occurs when a flexible metal diaphragm or membrane hydraulically flexes. In this type of an operation, only the membrane and the compression chamber come into contact with the gas. For this reason, the diaphragm compressor is ideal for applications that involve explosive and toxic gases. Membranes are designed to be durable and tough and able to withstand high temperatures and a variety of conditions. Diaphragm compressors can generate very high pressures and are used to compress hydrogen, hydrogen chloride, carbon monoxide, and compressed natural gas. Diaphragm compressors come in 1, 2, 3, or more stages. Each stage requires the use of one diaphragm. Picture illustrates the basic components of a diaphragm compressor. The basic components of a diaphragm compressor include inlet and outlet gas check valves, hydraulic fluid check valve, diaphragm or membrane, hydraulic injection pump, hydraulic piston, sight glass, piston rods, crankshaft, crankcase frame. Supporting equipment in a compressor system. When compressors are used in a process system, a wide assortment of supporting equipment is required as shown in picture. Some of this equipment, such as filters, drivers, and seals, will be described in other training. Here we will describe intercooler and aftercooler heat exchangers, safety valves, silencers, demisters, and dryers. Intercooler and aftercooler heat exchangers. The compression of gases creates heat in a compressor. Shell and tube heat exchangers, intercoolers and aftercoolers, have been added to the design to control high temperatures. As gas is discharged out of the first stage of a compressor, the intercooler lowers the temperature. This cooled gas is directed into the suction line of the second stage compressor. As this gas is compressed, creating more heat, it is discharged into the aftercooler before going to the receiver. Safety valves. Safety valves and pressure relief valves are used to relieve excess pressure that could damage operating equipment and hurt operating personnel. These valves are sized to handle specific flow rates and should not be replaced without ensuring that the replacement valves meet engineering specifications. Some safety valves automatically reset. Other types must be removed and mechanically reset. Silencers. Most compressors exceed OSHA, Occupational Safety and Health Administration, standards for noise pollution. Silencers are used to muffle some of the damaging noise produced by compressors. To be effective, mufflers should be mounted on the inlet and outlet of a compressor. However, hearing protection should always be worn when one is working on or near a compressor. Demister. A demister is a device designed to remove liquid droplets from gas. Demisters function along the same lines as a cyclone. As gas enters the top of the demister, it is swirled around the outer perimeter of the canister. Because liquid is heavier than air, centrifugal force brings it into contact with the outer wall. The heavier component falls to the bottom of the demister and is removed. Clean gas escapes out the discharge line on the top of the demister. Many positive displacement compressors would be damaged if wet gases were introduced. Dry air. For extremely dry air service, the discharge of a compressor is run through a dryer. Dryers filled with moisture-absorbing chemicals are called desiccant dryers. Alumina, molecular sieves, and silica gel are the most common types of chemicals used in dryers. Typical dryer operation uses parallel or series dryers. Both arrangements allow one dryer to be in service while the other is being regenerated. The regeneration process uses dry, clean, heated gas to strip the moisture out of the spent dryer. Oil separator. An oil separator may be used to remove oil from compressed gases. The receiver is the tank in which compressed gas is stored. Startup, shutdown, and troubleshooting of compressor systems. This picture presents a simple illustration of a multi-stage centrifugal compressor and a liquid ring compressor system. Each system is equipped with similar instrumentation and piping. The primary equipment found in this system is a compressor, receiver, dryer, air header, and modern process instrumentation. Only one system should be used at a time. Starting up and shutting down a dynamic compressor. 1. Perform valve lineups on compressor and associated equipment. Ensure that each valve is in the proper position before startup. 2. Check oil levels and bearing cooling water systems. 3. Check compressor controls for correct positioning. 4. Press start button on panel. Allow compressor to warm up unloaded. 5. Check for abnormal conditions on compressor. Check temperature, pressure, noise, and excessive vibrations. 6. Open suction line to compressor. Opening the suction line should load up the compressor as gas flow is established. 7. Monitor equipment until process fills lines. Starting up and shutting down a positive displacement compressor. 1. Perform valve lineup on compressor and associated equipment. Ensure that each valve is in proper position before startup. 2. Line up cooling water to exchangers. 3. Check oil levels and bearing cooling water systems. 4. Check compressor controls for correct positioning. 5. Reset manual unloader valve to unloaded. 6. Press start button on panel. Allow compressor to warm up. 7. Check for abnormal conditions on compressor. Check temperature, pressure, noise, and excessive vibrations. Troubleshooting a centrifugal compressor. If there is excessive vibration, there might be misaligned shaft, damaged coupling, damaged rotor, or bearing or seal damage. If discharge pressure is low, there might be leak in piping, low suction pressure, system demand exceeding design limits, or compressor not up to speed. If lube oil pressure is low, there might be low oil level, incorrect pressure setting, lube oil pump failure, or dirty filter or strainer. If there is high temperature on bearing oil, there might be restricted flow, oil needs to be changed, bearing failure, water in lube oil, or fouling in oil coolers. If there is driveshaft misalignment, there might be foundation shift, loose bolts on foundation, piping strain, or grouting washed out. If there is water in oil system, there might be ruptured tube in heat exchanger, condensation in oil reservoir, rainwater, or steam tracing leak. Troubleshooting a reciprocating compressor. Compressor will not start if there is a MCC or switchgear problem, low oil pressure shut down, there is no power to motor, or permissives or interlock not satisfied. If there is a noise in the cylinder, there might be loose piston, worn piston rings, piston striking cylinder head, or valve improperly seated. If there is high discharge temperature, there might be fouled intercooler, high inlet temperature, leaking piston rings, or wrong lube oil flow rate. If safety valve are lifting, there might be leaking suction valve on final stage, worn out rings on final stage, or discharge line restricted, the safety valve needs to be replaced. If there is a packing leaking, then packing needs to be replaced, or there is scored piston rod, or there might be dirt in packing, or because of pressure increase. If frame knocks, there might be cold oil, low oil pressure, wrong oil in system, or loose or worn crank pin. Compressor symbols. Each type of compressor can be represented by a symbol. This picture illustrates compressor symbols. Compressors differ from pumps in that pumps move liquids and compressors move gases. Compressors are used to transfer granular powders and small plastic pellets from place to place, to establish feed gas process pressures, to provide clean, dry air for instruments and control devices, and to compress gases such as light hydrocarbons, nitrogen, hydrogen, carbon dioxide, and chlorine. Gases and vapors are compressible. Compression decreases volume by moving gas molecules close together. Compressed gases will resume their original shape when released. Compressed gases produce heat because of molecular friction. The higher the pressure, the smaller the volume. Gas volume varies with temperature and pressure. Compressors usually can be classified into two groups: positive displacement and dynamic. Positive displacement compressors operate by trapping a specific amount of gas and forcing it into a smaller volume. These designs include rotary screw, sliding vane, lobe, and liquid ring, and reciprocating, piston and cylinder and diaphragm. The most common type of compressors, reciprocating compressors, work by trapping and compressing specific amounts of gas between a piston and cylinder wall. The back-and-forth motion incorporated by a reciprocating compressor pulls gas in on the suction or intake stroke and discharges it on the other. Dynamic compressors operate by accelerating the gas and converting the energy to pressure. They can deliver much higher flow rates than positive displacement compressors. That's all, gentlemen. I hope this training course have refreshed your knowledge regarding to compressors and compression system. Good day and good luck.